Hey Phys 1 kids, Campbell here. In our first video on oscillations, we're going to talk about some oscillation definitions and we're going to talk about springs. Now, what does a marble and a spherical bowl, a spring and a pendulum all have in common? Well, they all have an equilibrium position where they will be at rest if there's no net forces on them. Like for a pendulum, that's when it's straight down, right? When the pendulum is just straight down here and it's not being displaced from side to side, that is its equilibrium position. For a spring, that's the place where it's neither stretched nor compressed. And for my marble, you can see it's at the bottom of the bowl. If we push this object, whether it's a marble or a pendulum or a spring, away from that equilibrium position, then there's a net force that tries to move it back towards the equilibrium position. And this force is called a restoring force. And the repetitive motion, which my spring and my pendulum are still undergoing, is called an oscillation. So oscillation means repetitive motion, and it's caused because I have a restoring force trying to bring this object back to its equilibrium position where it's at rest. Now, if we graph this oscillation, it is in the form of a cosine function. So you can see that in my little oscillating spring down here, but you can also see that in the marble. So if I release the marble from a height above its equilibrium position, right, I've displaced it some position from the equilibrium position, and then it tries to go back to its equilibrium position, which would be at the bottom of the bowl, but it has some speed, right? So it keeps going. And so then it gets back up to some maximum height, which would be on the other side, and then back to the center of the bowl down at the bottom, but it keeps moving. And so it keeps following this oscillation. Now, a graph like this, that is either the form of a sine or a cosine, is called sinusoidal. And anytime I have a graph of motion for an object that's sinusoidal, we call it simple harmonic motion. You'll see me abbreviate it as SHM. A good example of simple harmonic motion is the motion of a spring. Simple harmonic motion is a periodic motion, which means it's that repetitive oscillation that forms that, in the case of a spring, a cosine graph. Back in energy, our last unit, we talked about briefly the spring force. The spring force, or the force of a spring, is equal to negative K delta X, where K is the spring constant, which is the stiffness, or how stiff a spring is, and the displacement is measured from that equilibrium position, the place where the spring is at rest. Now, if you think about units here, the unit of a spring constant is Newton over meters. The displacement is always measured in the SI unit of distance, which is the meter. Now, this is called Hooke's law. Anytime, that's really lousy, anytime we have this function that's linear, that the force increases linearly with distance, I have a spring that obeys Hooke's law. Hooke's law, this is Hooke's law, that a spring force is equal to negative kx. Now, the reason for the negative is the fact that the force is always opposite to the direction of displacement. When I stretch this spring out this way, right, there's a force that's trying to pull it back in the other direction. So that's what that negative here is all about. Amplitude, which is symbolized by an A, is the maximum displacement. So when I pull a spring out to some distance x and I let it go, that distance I pulled it out to is going to be its amplitude. It's not going to suddenly create more energy and have a bigger displacement. One cycle is a full to and fro motion. So like if I pull a spring out here, then and it goes back and then it comes back to that spot, that's a cycle. And the time for one cycle is called a period, capital T. We've talked about periods before when we talked about circular motion and the time to go around a circle once. Well, same thing for springs. The time for a complete cycle is a period. And of course, the unit of period is the second, and amplitude, of course, would also be a meter. Frequency is the number of cycles per second. So it's how much of the wave has passed in 1 second. Frequency, the unit of frequency is the hertz. And if you remember, actually, let's just put this down here, right? Period and frequency are inverses of each other. Just a little reminder from when we dealt with periods and frequencies back in circular motion. Another thing we need to talk about are the pluses and minuses of simple harmonic motion. Remember that in physics, whether I have positive or negative something, it's about the direction of motion. So if we want to talk about position, just like when we did kinematics, a positive position is if I am to the right of the equilibrium position, or negative if I'm to the left. Now, if I have a vertical spring, so here's my spring, let's say, and here is its equilibrium position, the position it would be at if I just let it hang. Now, if I stretch it and I pull it down here, we're going to call that a negative position because we're below the origin, and if we're up here, that's going to be our positive position. Remember that velocity is about the direction of motion. So when I'm moving in the positive direction, then I have positive velocity. So positive velocity is when I'm moving to the right, and negative velocity just means I'm moving to the left. And finally, we have acceleration. Now, acceleration, just like in any case, is always in the direction of the net force, which is the direction of the restoring force on a spring. And acceleration always has the opposite sign of the displacement for a spring. So it's positive when the displacement or the position is negative, and it's negative when the position is positive. Now, you're probably like, what? But let's think about that in terms of the motion. Remember in kinematics when we talked about if you're speeding up or slowing down and what direction you're going affected your sign of acceleration? Well, it still works here, right? If I am oscillating and I'm going this way, right? I'm slowing down as I get to the amplitude because then I stop and I'm going to start to come back. So I'm slowing down in the positive direction, and slowing down in the positive direction is a negative acceleration. Right? And then I reach amplitude and I stop and I start to come back. And so now I'm speeding up as I move towards that equilibrium position. So I'm speeding up in the negative direction, and speeding up in the negative direction is also a negative acceleration. And then I shoot past here, right? And as I compress, I start to slow down. And now I'm slowing down in the negative direction. Slowing down in the negative direction is a positive acceleration. I hit that amplitude, that compression, and now I'm going to cycle back towards the equilibrium. So now I'm speeding up in the positive direction. Speeding up in the positive direction is positive acceleration. So the signs of acceleration still can be explained the exact same way we explained them when we talked about kinematics and positives and negatives for acceleration. One thing that'll be important for you to do is recognize where things are at maximums and minimums. And so I'm going to start this spring oscillating and have a displacement graph. And as you can see, it makes sense that the displacement graph, when I reach amplitudes, right, I'm at a maximum. And when I go through the equilibrium position, I'm at a minimum. This is a graph of my position. Now, let's layer over that velocity. And I want you to look at where the velocity is a maximum and where it's minimum. Notice how they interchange locations. So when I reach a maximum for velocity, I'm at a minimum for position. So here I go. Here's velocity 0. Notice that when velocity is 0, I'm at the amplitudes. Now, if you think about the motion, that makes sense, right? Because when I reach amplitudes, I stop and I have to come back. But notice that the velocity speeds up and reaches a maximum when I'm at the equilibrium position. So I'm speeding up till I get to that equilibrium position, and now as I pass through that equilibrium position, I'm slowing back down till I get to the amplitude. And that's because the force, right, as soon as I get through that equilibrium position, then the force is trying to pull me back. So as I move, I speed up through the equilibrium position, and then the force tries to pull me back to the equilibrium position, and I shoot through it, and then the force pulls me back. So I have this opposite scenario for my velocity and my position. At the amplitudes where I have maximum position, I have 0 velocity. I stop because I have to turn around. Now let's throw an acceleration on top of that. Whoa. So notice that my acceleration, my velocity graphs are, again, interchanging at different spots. So when my velocity is 0, I have maximum acceleration. And when my velocity is a maximum, I have 0 acceleration and 0 position. So when acceleration is 0, position is 0? Is that because the force is 0? The other thing I want you to notice is where how acceleration and position differ from each other. They're always at a maximum at the amplitude. So my position is a maximum, my acceleration is a maximum at amplitude, but notice that their signs are different. So when one is positive, the other is negative. Okay, so on your note sheet, you will see a nice little picture of springs in different places. And I want you to write down where position, velocity, and acceleration are maximums and minimums. So if I have taken a spring from its equilibrium position, so here's my equilibrium position of my spring. That's a lovely spring. And I pull it out to its amplitude, right? My position is going to be the amplitude, so that's going to be a maximum. I stop at my amplitude. Right? Anytime I get to the amplitude, I start to come back the other direction, so I stop to change direction. So that's 0. So I reach what's called the turning point. My velocity is 0. I stop. And I'm in a positive position, so I have a negative maximum acceleration. Why is the acceleration max there? Well, remember that the force of a spring is equal to negative k delta x. So the bigger this value is, the bigger the force of the spring is. And Newton's second law, right, says force is mass times acceleration. So the bigger this is, the bigger the acceleration is. So when I reach amplitude, as I'm oscillating back and forth on a spring, when I reach the amplitudes, because I have the biggest displacement, I have the biggest force, and I have the biggest force, I have the biggest acceleration. Well, now I start to go back. I've stopped and I'm changing directions and I'm starting to move through the equilibrium position. And as I get to that equilibrium position, I guess I should have probably drawn this a little differently. How about there's my equilibrium position? As I get back to the equilibrium position, now my x value is 0. And if my x value is 0, right, that means my acceleration has to be 0 because there's no force. And it's at this point where I have a maximum speed. I've sped up because that force, I was accelerating that whole time towards the equilibrium position. So when I reach the point where I have no force, I have a maximum velocity, but I'm going to the left, so that would be a negative velocity. Now, my spring continues to compress till I reach the negative amplitude. So my position is a negative amplitude. I stop when I reach that amplitude, so I have 0 speed. And once again, because I have a maximum delta x, I have a maximum acceleration. But now I have negative position, which means I have positive acceleration. And we can go back and do this, right? I start to come back and I go through that equilibrium position again, right? That restoring force is trying to get me back there. And when I reach the point where I'm at my happy spot where x equals 0, that means my acceleration also is 0 because there's no force if there's no stretching or compressing. And I've reached a maximum speed. So I had accelerated to the point where the force went to 0. So I'm always at a maximum speed when I'm moving through the equilibrium position. Because once I get through that equilibrium position, there's a force that starts to pull me back and slow me down. And then, of course, I get back out to the amplitude, and we have the same case we had before. Now, how do I calculate the acceleration? What do you think? Think about how you would come up with a way to calculate acceleration for a spring with a known spring constant. Well, okay, there's a hint. Hooke's law and Newton's law. Well, Hooke's law, right, is that the force of a spring is equal to a negative k delta x. Newton's law, right, says that the net force on an object is mass times acceleration. Well, if I just have a spring oscillating, we don't have friction, right? Life is perfect and it's a frictionless environment, right? Then my net force is just the spring force, which means that my negative kx is equal to my ma, and so my acceleration is a negative kx over m. And again, once again, we can see that the signs of acceleration and position are going to be opposites of each other. Let's do one problem. So here's a 2 kilogram mass. I have a 400 Newton meter spring constant. If I displace it 12 centimeters, that's my amplitude, and I release it, what's the acceleration when I'm at an x of negative 7 centimeters? And then I also want to know what's my maximum acceleration. Well, so we just plug in negative k. This would be a negative 0.07. Let's put that in meters, right? We need to work in meters. 1, 2. And then divide that by the mass, which is 2. Our acceleration is a positive 14 meters per second squared. Now, if we go to the maximum, right, then instead of that 0.07, I'm going to put 0.12. And if I do that, I get 24. Now, the maximum acceleration, I didn't say, am I at positive amplitude or negative amplitude? So in this case, this could have been a positive or negative, which means my acceleration max is a positive or negative, 24 meters per second squared. Now, notice that neither of these accelerations are the same. So acceleration depends upon how much the spring is compressed while it's oscillating. Because acceleration is not constant, you cannot use kinematic equations. Never use kinematic equations for an oscillating system, ever. So then how do you find the speed of a mass on a spring? Well, so as we oscillate, we're interchanging our types of energy. At amplitude, right, where I have a maximum displacement, right, my spring potential energy is going to be a max, whether I'm totally compressed or out here totally stretched. But when I'm here at the equilibrium position, right, my x value is 0, which means my spring potential energy must equal 0. I have to be stretched or compressed to be storing potential energy. Now, what does this mean about kinetic energy if this is what the interchange is between is spring potential energy and kinetic energy? Well, if you can imagine at the amplitudes, right, I stop because I have to turn around and come back. So at my amplitudes, my kinetic energy is 0, is equal to 0. And in the very center, when I'm moving the fastest, remember I'm moving fastest when I'm going through that equilibrium position, I have a maximum kinetic energy when I reach the equilibrium position. And then in between these places, right, I'm interchanging. I have both spring potential and kinetic energy. So if I want to solve for speed on a spring, well, we want to say that the total energy, usually we think about it in terms of amplitude because it says, you know, how far the spring was stretched, is equal to the energy anywhere else. Now, if we're talking about the energy at x equals 0, then our equation would look like this, that the spring potential energy is equal to the kinetic energy. So we'd have 1/2 kx squared is equal to 1/2 mv squared. And so if I was to solve for v, I get the square root of kx squared over m, which of course we could pull the x out. So we'd have the x is times the square root of k over m. If I'm anywhere else, let's say I am, I don't know, there, somewhere at half the amplitude maybe, then the energy at the amplitude would be equal to the energy at, I don't know, x equals a over 2. I don't know, making that up. So then we'd have our spring potential energy initial at the amplitude, and that would equal the kinetic energy plus the spring potential energy when I'm at this partial amplitude, at half an amplitude or whatever. And so we do 1/2 kx squared is equal to 1/2 mv squared plus 1/2 kx squared. So wherever I am, make sure you take into account. But if we're looking at amplitudes, then these are my amplitudes for my initial kinetic energy. And anywhere else, whatever position I'm at, measured from the equilibrium position, that is what I use for my spring potential energy. So if I want to solve for speed, use energy. Don't use kinematics. The last thing I want to mention is energy graphs. Because of this x squared relationship with potential energy and the v-squared relationship with kinetic energy, an energy graph for springs is very interesting. So the total energy, right, at amplitude is all spring potential energy. So if you look at this oscillating spring up here, right, anytime I'm at amplitude, that potential energy, that blue curve here, is at a max. And when I'm at the equilibrium position, it's a 0. Makes sense, x is 0. And here's my kinetic energy, right? It's a 0 when I'm at the amplitudes. So here kinetic energy is 0 at the amplitudes, right? I stop, but it's a maximum up here when I'm at x equals 0 because I have a maximum velocity and I have no spring potential energy. Now, the really cool, interesting thing is the way the graph is shaped. It's not like I just have a graph that looks like this, right? Notice it's not a linear change as the spring oscillates. That's not the case. Notice it's a parabolic shape. So when I am at halfway, notice this is really interesting. When I'm at the amplitude over 2, notice that I don't have half kinetic energy and half potential energy. In fact, the place where I'm at half and half is actually somewhere greater than that, right here. Totally, totally interesting. So the shape of a energy graph for kinetic and spring potential energy for an oscillating spring is a parabola look like that. Pretty cool. I think that's very interesting. All right, we got some more notes to do in class, so fill out your WSQ and I will see you.